Welcome back to PPP. Now we are going to focus on some additional rules of Armstrong's axioms. So we can say they are additional rules, or we can say they are built from the basic rules of Armstrong's axioms. That's your wish. But now we are going to focus on additional rules of Armstrong's axiom. Yeah, let's dive right in. Additional rules for Armstrong's axioms. We have already learnt about three basic axioms, haven't we? The first one was reflexivity. Yeah, reflexivity. Second one was we learnt about something called augmentation. Third and last was we had about transitivity. We can derive some important axioms by using these three specific rules. All right, and they can be applied again and again in certain questions. That's why we are going to learn about them as additional rules. That's why we are going to learn about them as additional rules. Other than that, actually, if you have knowledge about these basic axioms, that's enough. But if you are doing bigger questions and if you are creating big databases for major companies, well, then you can't rely on the same functional dependencies again and again, right? I mean, same basic axioms again and again. Therefore, you will have to make some changes and come up with advanced axioms so that the work gets done quicker. All right. So, first of all, we are going to talk about the decomposition axiom. We are going to talk about the decomposition axiom. Decomposition. We are going to talk about decomposition axiom. Decomposition axiom is something that allows us to break down dependencies with multiple sets on the right side into simpler dependencies. What did I tell you? This allows us to break down dependencies with multiple sets of attributes. With multiple sets of attributes on the right side into simpler dependencies. Into simpler dependencies. This is why we normally use decomposition. All right. So how can I denote this using notation? Well, if you have a functional dependency that says x functionally determines yz, okay, you can decompose this into x functionally determines y, x also functionally determines z. This is how you apply decomposition rule from x functionally determines yz. This is how you normally do. I hope you understood. Now, let's see how we can derive something like this. Okay, how can we derive x functionally determines y and x functionally determines z from x functionally determines yz? Alright, shall we try? Now we can't use decomposition directly. Now we are going to use the basic three axioms: reflexivity, augmentation, and finally transitivity. Let's see if we can do that. Okay, so we need x functionally determines y and x functionally determines z. Okay, well, you can say before we derive this, I will teach you another important dependency. All right, that is a union dependency. After that, you will get the idea to do that by using your own brain. Okay, without relying on me, you will be able to come up with it. Okay, so first of all, we'll talk about union and derive that. Derive that. And then we can come back to decomposition. So union. Union is pretty simple. As the names suggest, it allows us to combine dependencies, combine dependencies with same set of attributes, with same set of attributes, with same set of attributes on the left side, not right side, on the left side, into a single dependency, into a single dependency that includes all the attributes, all the sets of attributes on the right hand side, that contains or includes all the attributes, sets of attributes, all the sets of attributes on the right hand side or right side. Well, the definition exactly tells the notation: if x functionally determines y and x functionally determines z, you can say x functionally determines yz. This is something like a reverse process of decomposition. From this, we can come to this means, that's called decomposition. From this, we can come to this means, that is union. So let's try to derive if x functionally determines y and x functionally determines z. Let's see if we can derive to x functionally determines yz. Okay. So first of all, shall we apply the augmentation property? Shall we apply the augmentation property? First of all, let's apply the augmentation property. What is the augmentation property? If x functionally determines y, we can say xz functionally determines yz. We can say xz finally functionally determines yz. So here we have x functionally determines y. Okay, I'm gonna say xz functionally determines yz. xz functionally determines yz. What am I doing? I'm augmenting the set of attributes z both sides, to both sides. This is the basic one that we have. Now we have come up with something different. Now the right side is set. The right side is set. No worries. Now we have to try and make xz. We have to try and make xz into x. That's the idea. Okay. Now let's see what can we do. Okay. Now let's apply the reflexivity theorem or uh, reflexivity rule. We know xz. Okay, if x functionally determines z, we can also say xx functionally determines xz. This is also augmentation. This is also related to augmentation. Xx functionally determines xz. Xx functionally determines xz. So I can say x functionally determines xz. Y x union x is equals to x. So this becomes this. We have x functionally determines xz, and here we have xz functionally determines yz. Surprise, surprise, we can use transitivity rule here. We can apply transitivity rule here. How? If x functionally determines y and y functionally determines z, we can say x functionally determines z. Here x functionally determines xz, xz functionally determines yz. So we can say x functionally determines yz. Instead of going to all this trouble, instead of going to all this trouble, you can directly apply this. This is what we call union rule. This is what we call union axiom in Armstrong's axioms. All right. Now, shall we go back to decomposition? Shall we go back to decomposition? Now you can actually do it by yourself. You can actually do it by yourself. Decomposition states that if x functionally determines yz, x functionally determines, then if x functionally determines yz, then X determines Y, X functionally determines Z. How can we do that? Well, here we are going to use reflexivity actually. X functionally determines YZ. Shall we break this YZ? YZ functionally determines Y. You can also say YZ functionally determines Z. Why is that? Because according to reflexivity rule, if X is a subset of Y, if X is a subset of Y functionally determines X. Or you can say vice versa. Y is a subset of X. We can say X functionally determines Y. Okay, this is reflexivity theorem. Here, X functionally determines YZ. Here, X functionally determines YZ. So, I am bringing YZ out. I am bringing YZ out. Why am I doing that? YZ is a set of attributes. There are two. Y is there, Z is there. So, I can say since Y is a subset of YZ, I can say YZ functionally determines Y. Similarly, since Z is a subset of YZ, I can say YZ actually functionally determines Z. Now we can apply transitivity rule and come back to the answers. Okay, so we have X functionally determines YZ and YZ functionally determines Y. This means X functionally determines Y. Similarly, X functionally determines YZ. So we can say YZ functionally determines Z. So we can come to a conclusion that X determines Z. Without going to all this trouble and the trouble I got you during the proving process, derivation process, you can directly apply decomposition axiom or decomposition rule. Now we are going to one of the last additional rule that we are going to look at. One additional rule that we are going to look at, that is called pseudo transitivity. Pseudo transitivity. Pseudo transitivity. Well, pseudo transitivity is something of a general form. It's a general form of transitivity axiom. General form of transitivity axiom. It's a general form of transitivity axiom. All right. This will help us to create a new dependency if we have a functional dependency and the second one and the second dependency that shares a common set of attributes. Okay. So what did I say? This helps us to infer or create a new dependency if we have a functional dependency. If we have an FT and a second FT that shares a common set of attributes. What does this mean? Well, let's say we have a functionally FT, we have a functional dependency X functionally determines Y, and let's say we have WY functionally determines Z. Well, by using this, if these two are present, you can say WX functionally determines Z. You can say WX functionally determines Z. Well, how can we derive this? This also has a simple application. This also has a simple application. So we have X functionally determines Y. Let's just augment W into this. WX functionally determines WY. Okay. So you will be asking like, wait. You taught us X functionally determines Y means you can say XZ functionally determines YZ. What are you doing here? What are you doing here? How come Zx functionally determines Zy? Well, we know what is represented here is union. X union Z is equals to XZ. I have already told you about that. In union, okay, in union, the order doesn't matter because union operator is associative as well as commutative. It is associative as well as commutative. So it doesn't matter where you add this, where you add this new, where you augment this new set of attributes. So it can be like this. Now, can you see something weird? Why? We have x functionally determines y and also wy functionally determines z. Now, wx functionally determines wy. So we can say like this, wy functionally determines z. After that, we can write this down here. See, wx functionally determines wy functionally determines z. So we can say wx functionally determines z. Without going through all this random work, you can directly apply pseudo negativity. Okay, this is more general form. Okay, because general form just said x functionally, transitivity said if x functionally determines y and y functionally determines z, you can say x functionally determines z. Okay, but in pseudo transitivity, pseudo transitivity, we are learning something new, where more general form actually. So this is how you can apply pseudo transitivity. This is the third axiom that we are using to find out some more FTs. All right. So before you go back to the, before you go and watch the next video, keep in mind you have to know the basic idea that I taught you about functional dependencies, FTs. Okay. We can have a set of initial attributes, the initial set of FTs, which is called F. All right. We can have F. And from a F, you can derive some more FTs. You can derive some more FTs. Or you can say you can infer some more FTs. For that, you use inferal code. Okay, inferal code. In this case, we are using Armstrong's axioms because it is sound and complete. We are using Armstrong's axioms because they are sound and complete. Perfectly correct, perfectly complete. Okay, so that's why we are applying Armstrong's axioms, and you will infer some more FTs. After you have those FTs, you can add those FTs. F plus implied FTs of F. Implied FTs of F. What is implied FTs of F? From F, what did you derive? From F, you can actually deriving some FTs, right? By using the inferal code. They are actually implied logically by F. So this set is called F plus. So keep this in mind before entering the next video. Why? I will be using this front and back and forth again and again to find out some very funny things. Okay, very funny things. So keep that in mind. Also, revise this. F is a subset of F plus. How this comes. Okay. Also revise this. F is a subset of F plus, or else you won't be able to understand the next video, because in the next video we are going to talk about equivalence of sets of FTs and how covering set of FTs work. Okay, covering set of FTs work. So keep that in mind. So first of all, go through this and then come back to the new video. All right. In the next video, we will look up, as I said, we will look at equivalence of FTs.
Thank you for exploring the additional Armstrong's axioms with us. If you enjoyed this video, give it a like and share it with others. Don't forget to subscribe and turn on the notification bell to keep up with the series. I'll see you in the next video. Until then, keep learning and stay curious. Bye-bye.